So we saw in the last section that we could talk about the actual area under a curve using a definite integral, but we don't know how to actually calculate that yet. So we want to see this relationship between the antiderivative and the area underneath the curve. So let's consider the area underneath the function f of x equals 2x from 0 to 3. So if we look at that function, it's a nice simple function. It just goes through the origin and then goes through 3, 6, and it's just going to be a triangle. So the area is going to be 1/2 the base, which is 3, times the height, which is 6. So ultimately, the area is just going to be 9. But if we notice that an antiderivative of this function is exactly x squared, and when you evaluate that antiderivative at the endpoint 3, it ends up being the area. But it's also going to have to do something with this initial starting point, but if you notice, the function at 0 is just going to be 0. So this is going to help us calculate the area. So let's try to do it a little more generally. Let's find the area from 0 to x. So now what I have is my function is going to go from 0 to x, and all I know is my output will be 2x instead. So this bottom base is going to be x. The height of my triangle is 2x. So my area is going to be 1/2 the base times the height. So if you simplify that, it's just going to be x squared, which is exactly the antiderivative of 2x. So this is something that's called the fundamental theorem of calculus, and it's one of our most important theorems we have, and we're going to go over. So what this gives us is a way to find the area under a curve or to evaluate a definite integral. So if we have a function as continuous on the interval from a to b, then if we want to find the area under this function starting from a, ending to b, we're going to find an antiderivative, f of x. We're going to evaluate at these two endpoints. So all this means is we're going to take the antiderivative, evaluate it at the endpoint, subtract the antiderivative evaluated at the initial point. And the nice thing is this capital F can be any antiderivative. You don't have to consider the most general one. It's going to be any one you want. So you can automatically pick C to be 0. So let's look back to this example. The area under the curve f of x from 2 to, or f of x equals 2 to the x from 0 to 3 would be then the integral starting at 0, ending at 3 of 2x dx. So we're going to find an antiderivative. The antiderivative of 2x is x squared. And then we're going to evaluate this from 0 to 3. So I'm going to plug in the top endpoint, 3. We're going to evaluate x squared at 3, so it's 3 squared. We're going to subtract off, plugging in the bottom limit. So subtracting 0, and again, you get 9. So you can see this connection between the two. So let's keep using this. Let's find the area under the given curve over the indicated interval. So we're going to start with the function y equals x squared minus 4x, and we want to find the area from -4 to -2. So if we want that area, we're going to have to take an integral. We're going to start at -4, end at -2, and we're going to integrate the function x squared minus 4x. So I need to find the antiderivative first. So if I take the antiderivative of x squared, it's x cubed over 3. Antiderivative of -4x is you increase the power by 1, so it's 4x squared over 2. And then the fundamental theorem of calculus is going to tell us to evaluate at these limits of integration. So you first plug in the upper limit, -2. So all the x's get replaced by -2. Subtract, plugging in the lower limit. So from this point on, it's really just a bunch of plug and chug and algebra. If you go through this whole simplification, you're going to find out that the area underneath this curve from -4 to -2 is 128 over 3. Okay. So let's try another one. Let's try the function y equals 3x, and we want the area under the curve from 1 to 4. So same process, I'm going to integrate from 1 to 4 of this function by first finding an antiderivative. So the antiderivative of 3 over x is the natural log function. And you got to have those absolute values. So we're going to evaluate 3 ln of x from 1 to 4. So you plug in 4 first, subtract plugging in 1, and then the really nice thing is the natural log of 1 is just going to be 0. So the area under the curve is 3 natural log of 4. So far everything we've dealt with in this section and the last section has had to have a positive function, but the fundamental theorem of calculus doesn't require that. It just requires continuity. So we think of it as area, but in reality your curve can be underneath the x-axis as well. So if that's the case, the area corresponding to it is going to be negative. So let's look at the function negative x squared from 0 to 3. That's our nice parabola. So it's going to be below the x-axis. So if I want the area of this function, I'm going to integrate from 0 to 3 of negative x squared. So an antiderivative of negative x squared is you increase it by 1, so negative x cubed divided by 3. And then the fundamental theorem tells us to evaluate it from 0 to 3. So first, you plug in positive 3 to get negative 3 cubed over 3. Subtract plugging in 0. And so that'll just simplify to negative 9 because this is just 0. So all this does, if you get a minus sign for the integral, it's going to tell you most of the area falls underneath the x-axis because it's absolutely possible some pieces are above, some pieces are below. And whichever one has more will tell you by the sign you get for the area. So let's just visually try to determine for a bunch of different options whether when we integrate from a to b we get something positive, negative, 0, and then we want to actually figure out what is this integral in terms of the area A. So each one of these pieces is going to be exactly the same. This has area A, this has area A. So I want to start at x equals a and go to x equals b. So they have exactly the same thing. So if I integrate from a to b of this function, I've got a piece that has positive area a and a piece that has negative area, which is negative a. So when you add these two together, you have one piece that's above, one piece that's below. They're exactly the same thing. It's just going to wipe out and the area is going to equal 0. In the next case, I have two pieces above, one piece is below, and each one of these kind of humps is exactly the same, even though it's not drawn that way. So if I want to integrate from a to b, my first hump is positive a, the next one is negative a, because it's underneath the x-axis, and the last one's above, so it's positive a. So two of these cancel, and you find your area is ultimately just a. So it's positive because you have more above the x-axis than below. And if we look at this last example, everything is below the x-axis, so you can automatically tell that it's going to be negative area. Now you've got 3 of them that all have area negative a. So when you look at the area from a to b of this function, you get negative a plus negative a plus negative a. The area is going to be negative 3a. So let's keep that in mind. We can still integrate the same way, but the function itself does not have to be positive. That is not important to us anymore. So now let's try to integrate from 1 to 4 of the square root of x minus 1. We're going to have to find the antiderivative of this, so let's go ahead and write that square root as a power to be able to reverse the power rule. The first thing I need to do is I need to take an antiderivative. X to the 1/2, you increase the power by 1. So 1/2 plus 1 will give you 3/2. Divide by the new power. Then the antiderivative of 1 is just going to be x. And then this gets evaluated from 1 to 4 because those were our limits of integration. So you can clean it up. Dividing by 3/2 is the same thing as multiplying by 2/3. And so you want to plug in 4 first for x, plug in 1, and subtract that from the bottom. So we can go ahead and go through all this algebra if you'd like. But if you take 4 to the 3/2, that's the square root of 4, which is 2. And then you'll cube it. And then 1 to the 3/2 is just going to be 1. So after lots of simplification, you're just going to end up with the area being 5/3. So the last couple examples we're going to go through are going to deal with the acceleration and velocity and position functions that we dealt with before. So we're given a function a of t is negative t squared, or negative 2t plus 6. We want to find ultimately the position function, knowing our initial velocity. So the velocity when time is 0 is 6, and the position when time is 0 is 10. So the thing we want to recall is that this s of t is the position function. V of t is the derivative of position. It's the velocity. And then a of t is our acceleration. It's the first derivative of velocity or the second derivative for the position. So if we want to start by finding v of t, I've got to undo this derivative I took to find acceleration. So I want to integrate a of t dt. So I want to integrate negative 2t plus 6, which is just going to be reversing our power rule. So you get t to the second over 2 plus 6t plus c. And that simplifies nicely to negative t squared plus 6t plus c. So I'm given a nice initial condition about the velocity. It's going to allow me to solve for this value of c. So if we plug in 0, we'll get 0 plus c. And this better have an output of 6. So immediately we get to find out that this constant c is going to be 6. So now we exactly know the velocity function. V of t is going to be negative t squared plus 6t plus 6. And so our ultimate goal is to find the position function. So now the velocity is the derivative of position. So to find the position, I integrate velocity, which is the same as integrating this function. So each one of these is just going to be reversing power rule. Antiderivative of t squared is t cubed over 3. 6t is 6t squared over 2. 6 is t. And then you get another arbitrary constant. I'm going to call this one d just to not confuse it with the c we found before. But if you use a plus c, that's not a big deal. And then you can do a tiny bit of cleaning up. 6 over 2 is just 3. And now I want to go ahead and use that initial condition I was given, that the position at 0 should be 10. So if we plug in s of 0 equals 0, you're going to get 0 plus 0 plus 0 plus just d. And this better equal 10. So immediately we find out d equals 10, and our position function is going to be negative 1/3 t cubed plus 3t squared plus 6t plus 10. So if you went and took two derivatives, you would see you'd end up with exactly the same acceleration function we started with. Okay. So now what we can actually do, knowing this relationship, is we can find the area underneath these functions to tell us about how far something travels. Because remember, this integral is really going to talk about that accumulation. So when we were dealing with cost functions, when you found the area under the curve of the marginal cost, which was the derivative, it told you what your cost was for this specific group of products. Same type of thing is going to happen when we deal with these position and acceleration functions. The velocity is giving you your rate of change. So remember, its units are like meters per second. So remember, its units are like meters per second. So because of that, when you find the area under the curve, you're going to just get how many meters you've accumulated over that time. So if we are given this velocity function and we want to figure out how far does the particle travel during the first 5 seconds, What we really want to do is we want to integrate and evaluate it from 0 to 5. So I'm seeing the accumulation of the velocity function over this interval. So we want to integrate from 0 to 5, which is going to be reversing a bunch of power rules. The antiderivative of t squared is t to the third over 3. Then you get 10t squared over 2, and we want to evaluate that from 0 to 5. So if you plug in 5 first, then you subtract when you plug in 0. Nice stuff happens because you'll get 0 and 0. And so after some simplification, and if you plug it into your calculator, you're going to see that the particle traveled about 104.17 meters. Okay. Now, if we want to figure out how far does it travel during the second 5 seconds, what we need to do is find the integral from 5 to 10. So this is my second group of exactly the same function. So all that does is it doesn't change the antiderivative in the fundamental theorem. It's just going to change the bounds that we plug in. So you plug in 10 first, subtract plugging in 5, and then if you go through and plug it in your calculator, you're going to see during the second 5 seconds, it'll travel around 229.17 meters.